Hi everyone and welcome to this tutorial on the use of federated learning within the AI4EOSC platform. Today we are going to start by introducing the concept of federated learning, stating the motivation for implementing this kind of technique in the scope of the European Open Science Cloud, and why are we interested in this tool when we are dealing with sensitive data in the EOS. So let's start with a quite simple example in order to introduce the concept of federated learning. This example is concerning the use of predictive keywords. As we all know, when we are writing in our keywords, we get some kind of tips for the next word that we are probably going to write. For example, here, this is my own keyboard. When I'm writing I'm coming, I get different possible options for the next word that I'm going to type. For example, here to, back, over. So how can we train a model in order to do so? Let's imagine that we are data scientists and we want to perform this kind of deep learning model for having this kind of predictive keywords. We all know that when we are trying to develop a deep learning model, we need to use as much data as possible. So our first approach is the most widely known, which is the centralized one, in which we are going to collect all data from all possible devices, and then we are going to train a machine or a deep learning model in the cloud in a central server with all the data available. In this approach, we need to centralize all the data in the same, let's say, in the same cloud machine, in the same server, and so on. Then we will train the model, and then we will return back the predictions to each device. For example, to each smartphone, to each tablet, to each computer, etc. In this case, we have a clear disadvantage, which is that data has to leave the terminal that has generated the data. In the case of smartphones, we need to centralize all the data in a single site, in a central server, in order to train the model. So we are dealing with different privacy concerns, with different privacy issues in this approach. So then we can think about a kind of edge computing in order to prevent this need of the data leaving the terminal that has generated them. So we can think now in this second approach, in which we will train the models locally in each device, and then we will train the model locally and perform the predictions locally. In this case, the data does not leave the terminal, the smartphone, the device that has generated the data, but we are using less data for training the models. So in this second approach, we have one advantage, which is that data does not leave the device, but we have a clear disadvantage, which is that we are using less data for training the model, so we are going to build less accurate models in this approach. So when we think about federated learning, we want to have the advantages from the two approaches. We want to use as much data as possible, in this case, all data available from all possible devices available, but we don't want data having the need of leaving the terminal, the device that has generated them. So that's why we introduce this kind of architecture of federated learning. What is the idea? The idea is data decentralization. We do not want data leaving the device or the center or the institution that has generated it, because we are now talking about predictive keywords, but we can think about different hospitals who want to collaborate in order to build an artificial intelligence model. Then they will have different data, different locations for their data, and they want to collaborate, but they cannot share their data among them, but also they cannot share their data with a central server, with a central location. So we are going to work with data which are decentralized in different sites. In order to do so, we are going to use a server-client structure. The architecture will be composed by one server and several clients. The clients will be the different data owners. In the case of the predictive keywords, each device will be a client. In the case of the hospitals, each hospital will be a client. Then the clients will only send to the server the parameters that they get when they train the model locally. So the clients will train the machine, the deep learning, the same machine or deep learning model locally with their own data, without the data leaving the institution, the device, the terminal that has generated it, and they will train locally and send to the server only the parameters obtained when the model is trained, the parameters or the updates of the parameters. Maybe if we think about an artificial neural network, we can think about the weights that define the network, and that weights will be transmitted to the server. Then the server will receive the weights, in this case, obtained from all the models from all the clients participating in the training, and will update the initial model. The model will be updated by aggregating all the weights. In order to do so, we can think about several aggregation functions, aggregation strategies, but the most simple one is based on the use of the weighted mean, in which we will be performing a mean weighted in base of the number of data of each client. We can think about federated learning as a special type of distributed machine learning with a special focus on data privacy, because we are protecting privacy as data is not shared, even for training purposes. In the federated learning architecture, we need to identify the potential clients that are going to participate in the training, and we must ensure that they have quality data and the same kind of data in all the devices. For example, in the case of the hospitals, we can find different problems because, for example, let's think about medical image. That will be the data that we are going to use in the demonstration. Maybe different hospitals capture the images using different devices. So we need to ensure the quality of all the images and that they are quite similar in order to train a global model. Let's move to the schema that I have briefly explained, but let's take a look to the schema step by step. So we have one server and we have different clients. Then the server will create the model that will be trained by each client. Well, even one client, one user can create the model and then send it to the server, which is the common approach. But we just need that one user, one client, and or even the server define that model and transmit it to all the clients. So we can start here by transmitting the initial model to all the clients. Then when all the clients have the same model to be trained, they will train it locally with their own data without sharing the data in any case. So this is the step number 3, where all the clients, all the data owners are training the model. Then in step number 4, each client send to the server. Here in step number 4, all the clients share with the server their local parameters once the model is trained. Then the server here in step number 5 will aggregate all the weights received. I'm talking about weights because we are thinking about neural networks, so I think that it's easier to understand, but we can think about the parameters that define a model, even the gradients in the case again of a neural network. So we will aggregate such model using an aggregation operator and then update the model. So when we have the model updated, we will resend it again in step number 2. We'll resend such updated model to all the clients, and the clients will again retrain the model, send again the weights to the server, and so on and so forth. So we will repeat this process a predefined number of rounds. Let's think about the advantages that we can get when we train a federated learning architecture instead the classic centralized approach. First, I think that it's clear that we are having quite advantages regarding security and privacy of the data used, because data are not sharing with a central server, but data are not sharing between the different clients that are participating. So we are ensuring collaboration between institutions, between devices, but we are not compromising the privacy or the security of the data by centralizing them, because we are working on decentralized data. In addition, we can get several advantages related to the reduced communication costs. We are saving energy, we are reducing the latency, because in the central approach we centralize all the data, then we train the model in the cloud in a central server, and we return back the predictions to each device, to each institution. But in the federated learning approach, the models are trained locally, so we are reducing the latency, and we are also reducing the computational cost, because in this case we are not training the model with all the available data in a single site, but the training is distributed in different sites. It's important to note here that the clients can be intermittent, and this can be a problem in some cases because maybe one new client will enter the training, but maybe other clients can disappear, for example, due to technical restrictions, to internet connectivity, and so on. Now, let's move to a demonstration on the use of federated learning within the AI4EOSC platform. For this demo, we are going to use a classical dataset based on the prediction of whether a patient shows or not pneumonia, based in a chest X-ray image, as the ones that we can see here in this slide. In order to perform the federated learning training, we have divided the initial trained dataset into 3 clients. Here we want to simulate that we have 3 hospitals that want to collaborate all together in order to build a robust machine or deep learning, in this case model, but they cannot share their data because when we are talking about medical data, we are talking about data that are quite sensitive. So in this case, it's quite important to be able to perform this kind of global models without sharing the data. So, in this case, we have split the initial training data into 3 clients for simulating these 3 hospitals, and we have performed a stratified train test random split as shown in this table here. The model performance is a multi-layer convolutional network that we have implemented using Keras, and now let's move to the AI4EOSC platform in order to perform the federated learning training. Here we have the AI4EOSC dashboard, in which we can see here the marketplace with the different models which are pre-trained, and we also have the tools in which we have the federated learning server. So in order to start the server, or in order to start any deployment here in the dashboard, we need to log in. In order to do so, in my case, I'm going to use the check-in via GitHub. So now when we are logging, we can start the tool, or even we can start a deployment. But let's go with the federated learning server. So we have different general configuration options for the deployment. In this case, we need to introduce a title, so let's call it Demo Federated Learning, and the description. We need to select also a service to run. We can always show here the help, but in order to select the service to run, it's quite important to see that when we are using Jupyter Notebook or Visual Studio Code, we will be able to change several things in our deployment, because, for example, if we just use the Fed server configuration, the service to run as Fed server, we will not be able to configure the training. So if we want to change anything or stop the training or start it again, we recommend to use Jupyter or Visual Studio Code. In this case, I'm going to select Jupyter, so we need to put a password, and then we can move to the hardware configuration. As you can imagine, the hardware configuration here is not quite important because we are just configuring the server, and the computation of the models will be done locally in each client. So we can go to the next step, in which we have the federated configuration. This is the most important part here, because we are going to select the options for configuring the federated server. So first, regarding the number of rounds, in this case, we are going to introduce 10 rounds. Then we have the evaluation metric that will be used for monitoring and validating the federated learning training. In this case, we will be using the accuracy because we have a classification problem, but we can introduce other metrics that are already here for us to be used, and we can introduce more than one. In relation with the minimal number of clients, in this case, we are using 3 clients, so in order to the federated learning training to be started, we will put 3 as the minimal number of clients needed. And finally, we have the federated aggregation strategy. I already explained the federated averaging, which was the aggregation strategy more used in a federated learning training. So it's the one that we are going to use in this demo, but we have here different options that are already defined using the Python library Flower. So now we are ready to submit our deployment. And now we can move, while the deployment is starting, we can move to the client side. I have already created 3 instances in which I have put the code corresponding to each of the clients that will be composing this federated learning architecture. So I have 3 virtual machines deployed in the cloud, one for client number 1, another one for client number 2 here, and another one for client number 3. They are running in different instances in the cloud. So let's take a look to the code of one of the clients, and then we are going to start the process. So first, we define the model that will be trained. The same model will be used in all the clients. This is quite important because we will then aggregate in the server side the different weights obtained from the different clients, but we need to have the same model trained. Then we define the flower client. Then, in order to do so, we define a class here, which inherits from flower client numpy client, and we define 3 functions, which are quite simple. First, we have the function for get the parameters, in which we use this function for TensorFlow in order to get the weights of the model. Then in the feed function, we set the same parameters for all the clients. We set the weights. This is also a function from TensorFlow. Then we feed the model, and finally we need to return the weights of the model, the number of data used for training, as you know, for performing the aggregation strategy based on the number of data used for training. And finally, we have the function for evaluating. For evaluating, again, we set the weights, and then we use the evaluate function from TensorFlow. Here we can, of course, change the parameters, change the metrics, and so on and so forth. So when we have defined the flower client, we just need to connect with the server. So in order to do so, we need to introduce here the deployment ID of our federated learning server. Then we introduce the ID of the deployment in which we have such server, and we are ready for connecting using start numpy client. So we need to introduce here the deployment ID. So let's go to our deployments. As you can see here, we have the deployment that we have just created now, which is the demo federated learning one, and here we have the deployment ID that we can introduce in our clients. So this client is now ready for connecting with the server. But first, of course, we need to start the server, so we access to our deployment. In this case, we used Jupyter Lab for this purpose, and we are going to start the federated server. We can take a look to the code in this deployment. We can take a look to the README, in which we have several information on how to use this federated learning server, but let's go to the point here. So we need to move to the folder in which the server is located with this fed server, and then we can run the server just by typing python3 server.py. As we can see here in this server side, we can see that the flower server is started, that will be running during 10 rounds as we previously established, and now the server is requesting the initial parameters from one random client. So now we can start connecting our clients. So let's move to client number 1 and client number 2, where we need to change the ID of this deployment that we are using to deploy the federated server. So we change this here, and as you may imagine, we have the same configuration for the flower client, but now saying client number 1. Also, we have the same model to be trained, and here we are reading the data from client number 1 because we are in this other client. And now let's move to client number 2 because we started with the third one, and now let's change again the unique ID of the deployment, because here we have client number 2 data, we have the same model as in the 2 previous cases. We define here the class flower client with named client 2, and then we change here the unique ID of our current deployment. So we need now just to activate our virtual environment in all the instances that we are using and run the code of the of all the clients in order to connect with the server. So let's start with the first one, Python 3, in this case client 1.py, and then the client will be connecting with the server. We can see here that the connection is ready, and if we move to the federated server, we can see that this has changed to evaluating initial parameters and federated learning starting. However, the federated learning process will not be started until we have 3 clients, because we established 3 as the minimal number of clients for training the model. So let's connect the other 2 clients, so Python 3 client 2.py, and we'll be connecting the second one. You can see here that the connection is ready, but nothing changed from the server side because we need 3 clients. So finally, Python 3 client 3.py, and we connect the third one. And now we can see that the process is starting. If we move to the server side, we see here that the round number 1 has started, sampled on 3 clients out of 3, and the process starts from each client side. We can see how we are training during 5 epochs in each client with the data from each client. So let's see what happens when this first round finished, and then we need to wait until the 10 rounds that we established as the predefined number of rounds of the federated learning training finishes. So let's take a look to the server side. We can see here that we have finished the first 9 rounds. In all the rounds we have sampled the strategy in 3 clients out of 3. We have received always 3 results and 0 failures. And now we are starting the round number 10. So if we move to the client side, we can see how the clients continue the training. We are just waiting for the second client. But we can start summarizing what we have done here. So if we think about this example here, we are dealing with sensitive data because, okay, this is a simulated example, but in a real scenario in which we are having medical images captured from 3 different hospitals, it's quite probably that these 3 hospitals would like to collaborate in order to build an artificial intelligence model, in this case a deep learning model, which can help them to perform better predictions for their patients. But probably due to technical, but of course due to security and privacy restrictions, because we are dealing with sensitive data, because these data are related to individuals, to different patients, it's probably that the hospitals will not be able to share their data. So here the federated learning architecture is quite interesting and quite important. So we have deployed the federated server using the AI4EOSC platform. As you know, we have used Jupyter Lab as interface, but we could have used others such as Visual Studio Code. We have considered here 3 clients, in this case simulating the 3 hospitals that will be collaborating, and we have distributed the data of the 3 clients in 3 different cloud machines that are external to the platform. We have obtained, as we are going to see now, robust results in terms of both accuracy but also in terms of the area under the curve, and we can see that in the test set of all the 3 clients. So let's move again to the server side. We can see now that the federated learning has finished. We can see here the time. We can see here the losses distributed. We can see how the loss is decreasing when the number of rounds increase. We can see it here, the first round, the second one, the third one, and so on. And we can see here also the accuracy aggregated. So we can see an increase of the accuracy here. And if we move to the client side, we have evaluated in the test set of each client the model aggregated, the federated learning model aggregated, and we can see the accuracy, which is quite high in all the 3 scenarios, and also the same for the AOC. So we have performed a quite robust model in a distributed way using the AI4EOSC platform and 3 machines created in the cloud in order to simulate the case in which these 3 hospitals cannot share their data and they need to work on their local machines or in their own cloud machines. That's all for this first tutorial on the use of federated learning within the AI4EOSC platform. We invite you to stay tuned to our social media, to our website, and to check the documentation of the AI4EOSC software stack that you can find in the description of this video. Thank you very much for your attention and see you soon.